What did you expect?
Like really tricky. Just, you know, more than
It
2
looks
weeks tricky.
deceptively simple.
Especially the ones that look easy.
Talk about it now. Okay, let's see. We were talking about the weak order Coxeter group. Just to remind you, and actually to introduce a piece of notation that maybe you've seen in the book, but I don't know if I've actually defined it in class. So we write something like this in a poset to mean that U is less than B, and there's nothing in between. But now I'm talking about the right through order, so I put an underneath. So we know that B covers U in the poset if B is given by multiplication by one of the generators, and it should be a generator that increases the length. By the way, this is sometimes denoted like this and sometimes denoted like less than with a dot in the middle. So this is the cover relation. And we know that if we want to go up in the weak order, you just multiply on the right by generators that make you longer. Okay, we're going to leave some room here for a couple of properties. Just to remind you some properties that we proved last time. Or maybe I'll just remind you what they are. We proved that the the weak order could be characterized by containment of the reflections that make U and V shorter. So these are the reflections that make U shorter when you multiply by them on the left. And so the weak order is characterized by this property. We proved this last time, and I will use it today. And we proved the prefix property, which also says that this is equivalent to saying that a reduced word for U is a prefix for a reduced word for B. This is actually the most important thing, the thing that we will use the most. And maybe the last thing that I'd like to remind you is this lifting property, which says that if we have here U, which is less than I had drawn it in the other way last time. So basically, if we had B bigger than SB and U bigger than SU, then B was less than U if and only if SB is less than SU. So you can add this one in. If and only if you can add this one. B less than U, if and only if SB less than SU. So this was the prefix property and the lifting property. Okay. So we're going to be using these properties of the weak order, and today I would like to prove for you a very nice result which tells us something nice about the weak order that is not true about the Bruhat order, which is that it's a lattice if W is finite or a semilattice if W is infinite. So what does that mean? That I tell you what a lattice means already in this class? I did, right?
Just
So
to be literal.
let me remind you what it is. So let me tell you what a meet-semilattice is. A meet-semilattice is a poset P such that any x and y in the poset have a unique greatest lower bound. Which is denoted like this, and it's called the meet of x and y. So this means that this guy is less than or equal to x and less than or equal to y. That's one thing. This means that it's a lower bound, but it's the greatest lower bound, and that means that anything that is a lower bound for x and y has to be smaller than this one. Okay? So that's what it means to be a meet-semilattice. Okay? Now, so now I remember that I did draw this. I did explain this to you, and I drew this picture for you. That one way of thinking about this is that if you want to know what things are less than or equal to x and y, then basically they're going to look like some section like this of the poset, right? Because if something is less than x and y, then anything below it is also less than x and y. And so the point is that there's a unique maximal guy here, and this is called the meet. So that's the picture you should have in mind. Now, in a meet-semilattice, that means you can take the meet of two guys. But what if you want to take the meet of more guys? Or maybe of infinitely many guys? Because remember that our Coxeter groups might be infinite, right? So you might want to take the meet of an infinite set. So when you can do that, this poset is called complete. So a meet-semilattice is complete if any set has a meet. So a greatest lower bound. And the subset is A, then we call this meet A. Now you might wonder whether this implies this, but if I'm bothering to put an adjective here, that must mean that this doesn't imply this. And so maybe a nice exercise for you guys is to find a meet-semilattice which is not complete. But what I want to prove is that the weak order is a meet-semilattice and it is complete. So that's the main theorem that I want to prove today. The weak order is a complete meet-semilattice. So that's what I'm going to prove. Okay, so let's take it easy. Let's first start with this, and then once we have proved that at least we have a meet of 2 guys, then we'll see how to take the meet of a maybe infinite set. Okay? So let's prove that any x and y have a meet. So our greatest lower bound. The way I'm going to do this, I'm going to do it by induction on the length of x. Okay? So what if the length of x is 0? Well, if the length of x is 0, then we know that x must be the identity, right? And what is the meet of e and y? Well, what are the things that are less than or equal to e and y? The only one is e. And so that's the unique greatest lower bound. So that means that there's nothing to say there. So that's good. Now suppose true for length less than length of x, and let's prove it for x. So here's my plan. Prove it for x and y. So my plan is that, again, I want to think that this is my poset here, which I'm just going to label w because the elements are the elements of w. Now I take x, I take y, and so let me consider the set of lower bounds for x and y. The things that are less than or equal to x and less than or equal to y. Let's call that E. So let E consist of the things let's call them A, such that A is less than or equal to x and A less than or equal to y. Okay? Now, so these are the lower bounds. Now, let me just take some random guy here in the highest level. Now, what I'm going to prove, of course, is that there's a unique guy in the highest level, which is the meet. But I don't know that yet, so let me just take some random one, and then I'll prove that that one is the meet. So let me take a guy here, call it z. So take z with maximum length. Okay? And I claim that this z is the meet of x and y. That's what I'm going to prove. So to prove that, basically I need to show that if w is in E, then w is less than or equal to z. Now, I want to ask you to stay on top of me with a mistake that I'm going to make. I'm going to try not to make, but when I make it, you should stop me. So I made a mistake, which is to write this. And I don't want to confuse you, because whenever I write this means Bruhat order. And so, since today I'm going to be talking about the weak order, then every time I have something like this, I should put R's underneath. And that means that I've made already a couple of mistakes, probably. So here, because here I meant R. I think that's the only mistake so far. Simplify the notation. So if w is less than or equal to x and y, then w is less than or equal to z. That's what I need to prove. So the way I'm going to prove that, so I'm basically taking all the w's in here. Let me do it first by doing it for the generators and then doing it for everything else. So first, I'll do it for generators. And then I'll do it for the other doubles. generator is less than or equal to x less than or equal to y, and I would like to show that it's less than or equal to z. Okay. So let's suppose that it isn't. Okay. And I want to reach a contradiction. Now, let's take a reduced word for z. Okay, so this is some reduced word. And the reason I want to do this is because, like I told you, usually the most useful way of thinking about the weak order is in terms of this prefix function. And so I want to say that z is less than or equal to x and y in that language. So if z looks like this, then it must be a prefix for, S1 up to sk must be a prefix for a reduced word for x. So let me just call this like this, and let me call this y. It's also bigger than z, so it can also be written as starting like this. Something like that. Reduced, reduced. All I'm using is that z is less than or equal to x, z is less than or equal to y. Okay? But now let's actually use these properties. For example, what does this say? S less than or equal to x. Well, what that means, remember, is that s can be thought of as a prefix for x. Now, s is a single letter, so all this is saying is that x can be written as starting with s. And that means that if I multiply x by s on the left, since x can be written as starting with s, that's going to make me shorter. And I know what this means because the exchange property tells me what this means. It means that sx can be written as just removing one of these generators. I'll just define a second y. The one that I remove has to be one of the s primes. If I have this, I can solve for x and get x equals s, s1 up to sk, s1 prime, a prime, up to s prime. Now, why is it that the variable that I removed here has to be one of the primes? Well, you see, if it wasn't one of the primes, if it was one of these guys, then I would have two expressions for x that agree in the primes and disagree in the beginning. And what I would get if I do that is that sz would be less than z. So maybe I should write this out. So why did I say that sx had to be like this and not like this? Because it also could be that I had something like this. Yeah, so either I had something like this or I have something like this, but I want to prove to you that this cannot happen. Why is it that this can't happen? Because I have a different expression for x that looks like s1 up to sk, and then it finishes in the same way. Okay? And so what I will obtain is that s1 up to sa hat sk equal to S1 up to Sk, but S1 up to Sk is Z. Yeah? And so what this says is that you can write Z as starting with S, but that's a contradiction because we're assuming that Z cannot start with S. So this proves to me that this is a contradiction and that what happens is actually this. Any questions about that so far? Now, I want you to look at this expression for x. X has length k plus I, right? Now, here I have a different expression for x, where I added this s, and I removed this sa prime. And so since I kept the length fixed, that means that this is also a reduced expression. This is a reduced expression. So let me write it over here. We saw that this can't happen, right? So this is a reduced expression. Now, what that means is that I can't reduce it at all, and that means that this thing right here is also reduced. Because if this were reducible, then I would be able to reduce x also. So if this long word is reduced, that means that this shorter word is also reduced. Okay. Now, this is reduced, and it's an expression for what? Reduced word for, well, this is S times Z. Okay. And so what did I just do? I took a reduced word for X and found SZ as a prefix of it. And that means that SZ is less than or equal to X in the weak order. Now, of course, there's nothing special about X here. I could do exactly the same argument for Y. SZ is less than or equal to Y. Now, why is this a problem? This is a problem because I said that Z was the longest lower bound of X and Y, but here I found a lower bound for X and Y, which is longer. Why is it longer? Because Z can't start with S. I mean, a reduced word for Z cannot start with S, and so that means that this is a longer word, and this contradicts the choice of Z as the highest lower upper bound. So this contradicts. That L of Z was max. So that proves my first case of this claim. This claim is true for generators.
We didn't really use the induction for that part.
That's true. I haven't yet used the fact that I'm doing induction on the length flex. I'm only going to use the induction for part B. So far, this is just a straight up proof for X and Y. So, having done that, let's do the case B. arbitrary, but of course less than x and y, right? Okay. So, what is it that I want to do here? Let me draw a picture for you. So I can imagine that this is my big flow set. Here's x, here's y, and then E looks like this maybe. And Z is one of the highest guys in here. So V is less than x, V is less than y. And I'm just taking some W that lives inside here. Okay. And what I would like to prove is that W is less than Z. Less than or equal to Z. And the way I would like to do it is by induction. Okay. By induction on the length of x. So somehow, my plan is the following. My plan is to, since I want to induct on the length of x, I basically want to have a picture like this that's similar but a little bit lower. I need to be able to lower x so that I can use my induction hypothesis. And we know that the way we lower things in this flow set is by multiplying by generators. And so the thing now is choosing the correct generator so that I can lower things here. That's my plan. And the way that I want to do it, you see the thing about this is that I want to lower x, probably I want to lower y also, and maybe I want to lower w in a way that the picture looks similar. And this should remind you of this lifting property here. This is the kind of thing that we want to have. The lifting property is something that allows us, if you have a reflection that sends u and v down, that means you can lower the relation between v and u. That's the kind of thing we're after. Now, here I also have relations between w and x and w and y, and I want to lower those, and so what I'm going to do is take a reflection that makes w lower. And then I'll show that actually it makes everything else in my picture lower as well. So, how do I take a reflection that makes w lower? Well, which ones make w lower? So I'm actually going to need some nice colors here. I want to obtain something like this. Now, if I want SW to be lower than W, then what property does S need to have? Well, basically, I can think of this as W starting with the letter S, so that when I multiply by S, I become lower. And W starting with the letter S means that W is bigger than S in the weak order. So I take S less than or equal to W in the weak order. And that forces SW to be less than W. But notice that W is a lower bound for x and y. So if S is less than W, then S is also less than x, less than y, and I can extend this. So, because S is less than W, S is less than x, and S is less than y. And each one of these implies that I have edges going down like this. In my post. So, in symbols, SW is less than or equal to W, sy is less than or equal to 1. Now, this is where my induction is going to come in, because I know that xs, sx, and sy are lower than x and y, and I do know that they have a meet, because they're lower. So, let's see what's the nicest way to draw this. Let's take their meet. Now, what do you think their meet is, by the way? The meet of sx and sy. If I forced you to guess, you would probably guess that it's sz. And so hopefully that's true. Let's put it close to sz, but we don't know that it's sz. So let's call it z prime. Z prime is, well, so I want to say that it's right here. And I will prove it, but not yet. So for now, let's call it z prime. So z prime is the meet of this guy and this guy. So let z prime be the meet of sx and any questions about this so far? Now, again, so what I would like to show is that this is actually sz, and I will show it. Now, to know that, maybe I should know whether multiplying z prime by s makes me bigger or smaller. So what is it? Does z prime go up or does it go down? While you think about that, let me copy this picture. Let me copy part of this picture over. So the question is sz prime bigger or smaller than z prime? And I'll copy the part of the picture that I need here. X, y. What do you guys think? Whether z prime is bigger or smaller than z prime depends on whether z prime can or cannot start with s. Now, can z prime start with s? Well, it depends. Is it true that s is less than or equal to z prime? That's what I'm asking, right? I'm asking whether z prime can start with s or not. Well, the thing is, if s was less than or equal to z prime, then s would be less than or equal to sx. If this was true, then this would be true. And if this were true, that would mean that when I multiply sx by s, I would become smaller, but actually I become bigger. This is not true, since x is bigger than sx. So that means that this is not true, and because this is not true, that means that when I multiply by s, I become bigger. So this is a contradiction, and that says that s z prime is bigger than or equal to, is bigger than z prime. Okay? Now what can I say? What can I say when I have something that looks like this? This is exactly the setup of my lifting lemma, right? Whenever I have a nice parallelogram that wants to be completed, I want to complete it. Because these guys represent multiplication by s, that means that I can lift this relation to this relation. So I can lift z prime less than sx to x, I can lift it to s z prime less than or equal to x. And I can lift z prime less than or equal to y to s z prime less than or equal to y. I take these guys and I lift them to look like this. So what have I just proved? Well, I have proved that s z prime is a lower bound for x and y. So that means that when I multiply z prime by s, I land inside E. Can I conclude from that that this is actually z? I conclude that s z prime is higher than z prime and it lives inside here. But that doesn't necessarily imply that it's z. All I know about z is that it's the guy with the longest length that lives inside here. And that means that because s z prime lives inside there, it has to have length at most the length of z. So this is because this is a lower bound for x and y, and the largest length of a lower bound is this one. So this is one thing, which takes me a little bit closer, because remember my goal is to prove that these two things are equal, and at least now I have one inequality that tells me, well, maybe. Now, the next thing I'll do is do the same analysis, but you see, I use this analysis to use x, sx, z prime, sy, and y. But I haven't used z. And so let me make a similar analysis. This is one piece, but now let me take x, y. I know z is less than or equal to both of them. Here's sx. Here's sy. And what about sz? Is that higher or lower? Well, to know whether sz is higher or lower, I need to know whether s is less than z or is not less than z. Now, I would like to claim that sz is lower. To prove that, I would need to prove that z can start with s. Now, do I know that s is less than or equal to z? What do I know about s? S lives down here. S is less than x. S is less than y. Can I conclude that s is less than z? The only reason I can do that is because I already did the case A for generators. For generators, I know that if a generator is less than x and is less than y, then it also has to be less than z. So since I know that s is less than or equal to x and y, and it's a generator, that means it's less than or equal to z, and that means that this guy gets lower, and so my picture looks like this. Okay. So now I look at this piece of the picture, and I say, okay, well again I have some parallelograms that would like to be completed. And I call this the lifting lemma, but that name is a little bit misleading, because remember that this, let's go back over here and let's make the camera go over here and show it. What does this thing that I call the lifting lemma looks like? Well, it tells you that if you have two parallel edges, where by parallel I mean that I multiply by the same s, then the lower edge can be lifted to the upper one, but also the upper one can be lower to the bottom one. So this is kind of a lifting lemma, but also a lowering lemma. Now, first case I wanted to lift. In this other case I want to lower. And I can do that. I can lower these guys to become these guys. Okay. So I can lower that z is less than or equal to x and y to imply that sz is less than or equal to sx and sy. Now, why is that a good thing? Because you see, what are the things that are less than or equal to sx and sy? Remember that I'm taking this induction hypothesis that says that I already know that sx and sy have a meet. And so if sz is less than or equal to both of them, then sz has to be less than or equal to their meet. And what is their meet called? Their meet is called z prime. So with these two pieces of the analysis, I have shown these two inequalities. But let's look at what these two inequalities mean. And let's look at them looking at this picture. What does the first inequality say? It says when you take z prime and you multiply by s, so you make it higher, it's still not as high as, it says most as high as z. What does the second inequality say? It says when you take z and you multiply it by s, which makes it lower, it becomes less than or equal to z prime. Okay. And you see these two inequalities are pointing in the opposite direction and are going to show these two things. How exactly do I make this precise? Well, by rewriting this one as, let me subtract 1 from both sides. So what's L of z minus 1? It's L of sz. That's L of z minus 1. And what's L of sz prime minus 1? It's L of z prime. And now if you look at these two inequalities, this one tells you that sc is less than or equal to z prime in the poset, and this one tells you that this thing is not lower than this in the poset. So if they're comparable, and these two inequalities point in the opposite way and tell you this must be the same else. As z is equal to z prime. Okay? And that allows me to add this edge that I wanted to add. So our guess was right. The meet of sx and sy is sz. But what is it that I'm trying to prove? I'm trying to prove that w is less than or equal to z. How do I know that w is less than or equal to z? The reason I know that w is less than or equal to z is that, again, these two guys differ by the same thing. And I can lift SW less than Z prime to W less than Z. Now, I should say, why is SW less than or equal to Z prime? Because Z prime is the meet of Sx and Sy. So let me do this a little bit more slowly. This is the kind of thing where I can write symbols, but it's it's more useful to look at the picture. Thing is, yeah, what I'm going to ask you to do is just to look up and watch this, and let's do this as a video. Okay, so all I'm going to do is fill in relations in this picture, and the last relation that I'm going to fill in is the one that I want, which is W is less than or equal to
We just showed that SV is equal to Z prime, so isn't that already there?
So that proves that this is equal to S. So what I need to justify now is why is SW less than SZ? So that I can lift that. But that's okay because the thing is, I'm going to need a new color. So first of all, I know that W is less than X and W is less than Y. That's by definition. W less than X, W is less than Y. Now, each one of these things can be lowered to say that SW is less than SX, SW is less than SY. Now, if you're less than SX and you're less than SY, and those guys have a meet, that means that you're less than their meet. So that implies that SW is less than the meet, which is Z prime, which is SZ. And now, if SW is less than SZ, then you can lift this to W. So that's the proof. Now, if you didn't follow that, then watch the video and watch me do this again. I hope I'm making the point to you that, I mean, if you try to read these proofs in the book, you might find them a little bit hard to follow unless you draw a picture like this. And I should warn you that, this is the way a lot of these proofs go. It's a lot of kind of diagram chasing. And then when you write it in a book, then you have to write equations. But I think it's more useful if you watch the video of what I just did again. Just chase arrows around. But my last thing that I showed, my last edge that I drew was W less than Z, which is the one that I wanted to show, which proved my claim. And my claim proves that Z is the mean of X and Y. And that proves that this is a meet-semilattice. We should probably stop there. Maybe I'll just tell you that once we have that it's a meet-semilattice, actually the complete part is not very hard, and we'll do it last time. But really, the hard work is what we just did.
Does the complete depend upon finiteness? You said some distinction about finiteness.
So the question is whether the completeness depends on finiteness, and the answer is no, because Coxeter groups can be infinite, and so you might want to take meets of infinite sets, and you can do that not because the Coxeter group itself is finite, but because it has this nice grading.
And the top element has finite.
And so now there might not be a top element because again this might be an infinite group that lives infinitely high. But if you know which guys you're taking the meet of, then those are at a finite height, and then that finiteness is what allows you to do this.
So my problem is that a complete meet-semilattice is a complete lattice.
If it has a top element.
It's like a Unitarian ring condition, right? you can sort of give asterisks or some sort of notation to suggest what might be hard and therefore maybe more challenging and that sort of thing. Like
For the homework, you mean?
Yeah, yeah. Because we don't know.
Yeah. But that's very much on purpose because I feel like one of the things that you have to learn is to find out whether a problem is difficult or easy. And actually, I on purpose order them in a completely random order so that you won't know.
Okay, but
Now,
okay.
if you come and talk to me and
Yeah.
tell me your ideas, I'll be happy to help you. But
Right.
but I do want this to be part of the.
How about during the solution phase, indicate what
This was a very difficult problem. Okay, sure.
Okay, yeah.
I mean, that's very subjective, of course, but yeah, sure.
Yeah. Well, this is part of the learning process because we hardly know.
It's not broken.
And then by the time you try to figure out 5 problems, you sort of quit. No more time left.
Yeah, it's like 3 times.
Yeah, and I mean, the problems that I'm assigning, all of them are within your reach as far as
Yeah.
the tools that you need.
You can
But
believe
some of
that.
them are very hard. I mean,
Yeah.
that's true.
Yeah.
That's why I give you 10 and I give you some choices.
9, kind of deceptively easy, and with the finite dimensional cases, it's pretty straightforward on induction.
Which one was
the
that?
anti-chain? It's always finite in the Ruhart ordering, but it's kind of.
Yeah, that one seems easy because it's only one sentence, right? But it's
No, yeah, no. I mean, for the finite dimensional cases, I actually saw in Bona a proof for the finite dimensional case. And so in that case, this product space is pretty straightforward on induction. But for this one, it's not so clear.
Yeah. I mean, so I'll post the solution, but yeah.
Yeah.
That is one of the harder